hydrophilic aromatic substitutions. And the next one that we're going to look at is a nitration reaction. We're going to nitrate the aromatic ring. Now, those of you in the lab that's taking the lab will be doing this reaction in lab tomorrow. I'll first put up the reaction and then we'll go through the mechanism. We're going to take a benzene ring. We're going to add nitric acid and we're going to add sulfuric acid. And this will put a nitro group, which is NO2, onto the ring. As byproducts, I'll just go ahead and show we get a hydronium and we get HSO4 minus as byproducts. But we have nitrated the ring, we put an NO2 group onto the ring. Now let's take a look at our mechanism. Let me draw out the nitric acid and the sulfuric so we can see them. This is nitric acid. And here is sulfuric acid. First thing that's going to happen is these two are going to react. Anybody want to tell me what's going to happen? What do I always tell you? When you got a strong, when you see a strong acid, look for something to protonate. Now, I have two strong acids up there. Both of them cannot be the acid. One wins, one loses. Which one is the stronger acid? Sulfuric is the strongest. So, sulfuric being the stronger acid, it wins. It's going to be the acid. So, the nitric acid actually has to be the base. Like I said, they both cannot be the acid. The stronger one wins and the other one has to be the base. Now, whenever we have that strong acid, we're going to look for something to protonate. Something's going to go get the proton off of the acid. On the nitric acid, any of these three oxygens could go get the proton off of our acid. But if we use the OH, now again, any of the three can do it, but if we use the OH to come and get the hydrogen off of the acid, then that's going to give us a water molecule sitting there. We know water molecules are good leaving groups. And so part of the time that's going to happen. All acid-base reactions are reversible, so if one of the others get protonated, they'll come right back off eventually. But if we protonate the OH, like I said, we have a good leaving group there. We've got a water molecule. Water molecules are always good leaving groups. I'm going to take the negative charge on the oxygen. We're going to take, water could leave off on its own, but it'd be nice if we have some help. So this oxygen is going to kick electrons in to form a double bond, and that pushes the water off. So we get a water molecule, and we've made this species. This is called a nitronium ion. This nitronium ion, this is our electrophile. This is the electrophile that's going to react with the aromatic ring. You can see it's got a full plus charge. We said electrophiles have full positive charges or large partial positive charges. So now that we have the electrophile in hand, the mechanism is the same for all of these electrophilic aromatic substitutions. When we have the electrophile, they all react the same with the benzene ring. It's just getting to the electrophile is the only difference in these mechanisms. So let's take our aromatic ring, our benzene, and the nitronium ion. And we're going to take a pair of electrons out of one of the double bonds of the aromatic ring. That's going to come and add to that nitrogen. Now that nitrogen already had 8 electrons, so to avoid breaking the octet rule, we need to kick a pair onto one of the oxygens. So one of those 2 carbons of the benzene ring here from that double bond, one of these 2 gets the electrophile, the other one gets the plus charge. Now, we need to pull off, just like we did with the chlorine there yesterday, or the generic electrophilic aromatic substitution I went through. We need to get the hydrogen that's on the carbon where we just put our electrophile. That's the hydrogen we want, because if we can get that hydrogen off, then we can get back to an aromatic ring. We went from aromatic to non-aromatic, and so we want that aromatic ring back. The best base that we have in there is the water that left a moment ago. So that water is going to come and grab the proton, and electrons kick toward the plus charge and reform that aromatic ring. And we put the nitro group on. We got our aromatic ring back, and we have done put a nitro group, substituted a nitro group for one of the hydrogens. We get a hydronium here, we get our acid. All of these reactions use an acid as a catalyst, and so we do get the acid back. We have nitrated the ring, put a nitro group, NO2. Questions on the nitration? Okay, let's look at another group putting onto the aromatic ring. We're going to look at a sulfonation. Let's look at the reaction here to start with, and then we'll go through the mechanism. We're going to take an aromatic ring. We're going to react with sulfur trioxide. This will be done in the presence of sulfuric acid. And we put a sulfonate group onto the aromatic ring. There is the sulfonate group drawn out. So this is another electrophilic aromatic substitution. Now, the sulfur trioxide you don't have to actually add sulfur trioxide. You can use just sulfuric acid by itself. Sulfuric acid will make sulfur trioxide over time. If it's just sitting there, it will make sulfur trioxide. So we don't actually have to add the sulfur trioxide. You can buy sulfuric acid with sulfur trioxide in there, and when you buy it together, this is called fuming sulfuric acid. And you'll have, looks like smoke coming up off of it. It fumes. That's called fuming sulfuric acid. So you can buy that, and we can add that in. Or like I said, we can put just sulfuric acid. I don't have to have the sulfur trioxide. We can use just concentrated sulfuric acid. Let me show you how the sulfuric acid, if you take 2 equivalents of sulfuric acid, this is in equilibrium. Sulfuric acid is in equilibrium with sulfur trioxide, a hydronium ion, and HSO4 minus. So, like I said, sulfur trioxide will make some, sulfuric acid will make some of the sulfur trioxide. So we don't have to actually have that in there. We can use just concentrated sulfuric acid, and we will get the same product. Doesn't hurt anything. It actually, helps to put it in there. It makes the reaction faster. We don't have to wait for the sulfuric to make the sulfur trioxide. So it's faster to add it in there. So let's look at our mechanism. And let me draw out the sulfur trioxide. There's the sulfur trioxide. There is a large partial positive charge on the sulfur. The sulfur trioxide is our electrophile. So we don't have to go through and try to make the electrophile. We already have the electrophile in hand. So we're going to take a pair of electrons out of one of the double bonds of the aromatic ring. They're going to come out and add to the sulfur. Sulfur has got 12 electrons there around it. Sulfur can accommodate 12, but it can't have any more than that. So we're going to kick a pair out onto one of the oxygens. So we went from our aromatic to a non-aromatic. Again, even that non-aromatic, even though it's non-aromatic, it's not too bad because it does have resonance. I think I forgot to tell you the name of it yesterday. It's called an rhenium ion. It has resonance with the double bonds there. Not important, but it's called an rhenium ion is the name of it. So it's not so unstable, but it's not as stable as an aromatic. We'd like to get our aromatic ring back. We need to get the hydrogen off of the carbon where we just put our electrophile. We can use HSO4 minus that we have in there. Sulfuric will give some of the HSO4 minus. That's probably the best thing that we've got. I don't think this oxygen can reach over here and grab it. It's too far away. I wouldn't count it wrong if you want to use that one. But I'm going to show it in 2 steps. We get our aromatic ring back, that sulfonate group needs to pick up a proton, so we just made sulfuric acid, and then that can easily reach and get the proton off of the acid. So that gives us our sulfonate group. Onto the aromatic ring. Don't forget that hydrogen with the sulfonate group. The nitro group doesn't have a hydrogen on there. Sulfonate does. Okay, questions on the sulfonation. We can put a sulfonate group on. Still putting more groups on. We're next going to look at a Friedel-Crafts alkylation. We're going to look at putting an alkyl group onto the aromatic ring. Now, as I've mentioned in the past, when you see people's name associated with a reaction, that's a very important reaction. Make certain that you know those. These Friedel and Crafts, these 2 guys won a Nobel Prize for their work. So these are important reactions that we're going to be looking at. We're going to do one of these in lab on Monday. Let's look at a general reaction generic here to start with. We're going to take our aromatic ring. We are going to take an alkyl halide. We're going to put in a Lewis acid catalyst. And we will put an alkyl group onto that ring. We get an acid as a byproduct. We get HX there, some acid as a byproduct, depending on what the halide is. So HCl, HBr, something like that. But we have put an alkyl group onto the ring. Now, any Lewis acid will work. Some of the most commonly used Lewis acids, I'll just review you in a moment. We covered a lot of Lewis acids in Organic 1, but I'll review you for a moment. So some of these catalysts that could be used: aluminum chloride, aluminum bromide, iron chloride, iron bromide, titanium chloride. It has 4 chlorines. BF3. Some of those are the most commonly used Lewis acids. Any of those will work. There's lots of others, but those are the most commonly used Lewis acids. Let's take a look at a specific example, and we will go through the mechanism. take an aromatic ring and I'm going to react it with this alkyl halide. And we'll do this in the presence of the Lewis acid. Now the first step of our mechanism is that alkyl halide reacting with the catalyst. So the first step of our mechanism, we know that iron has a large partial positive charge, and the chlorine is on the alkyl halide is going to give a pair of electrons to that iron. So that's the first step of our mechanism. It is the same as what we did with the halogenation that we did yesterday, at the end of class yesterday. We reacted a chlorine molecule with the Lewis acid. Now if you follow your arrow, you could get your charges on. The initial tail becomes more positive by charge, so that chlorine will now have a full plus charge. Final head becomes more negative by charge. That iron has a full negative charge. Now a chlorine with a plus charge, just like we had yesterday at the end of class, it's not happy. There's lots of things that's not making it happy. It's got a plus charge. It's an electronegative atom. It does not like having a plus charge. It's got two bonds. Halogens want to be monovalent, and we've got it divalent, so it's not happy. Going to break apart. We could break the chlorine-iron bond that we just formed and go back to where we started. And all acid-base reactions are reversible, so that could happen. Or we could break it apart on the other side. We could break the carbon-chlorine bond. Take those electrons onto the chlorine to get rid of that plus charge. So that chlorine is now neutral. The other piece that we have a carbocation now. That carbocation that we have is our electrophile. That's what's going to react with the aromatic ring. So let's react it with our aromatic ring. Same. Now the mechanism is the same as what we've been doing for all of these. We're going to take a pair of electrons out of the double bond of one of these double bonds of the benzene ring, and we're going to add that to the electrophile. It's going to attack the carbon with the plus charge. So one of those two carbons of the double bond gets the electrophile, and one gets a plus charge. We have made our rhenium ion. Now we want to get back to the aromatic ring, and I also need to get my catalyst back. It's not a catalyst if you don't get it back. So that anion that we had over there, it's going to come and grab the hydrogen on the carbon where we just put our electrophile. We always need to get rid of the hydrogen that's on the carbon where we just stuck our electrophile. I'm going to take a chlorine off, come and grab that hydrogen, and the electrons kick in to form the double bond. So we get our aromatic ring back. Aromatic, there is our product, and as a byproduct, chlorine grabbed the hydrogen, so we made HCl as a byproduct, and I also got my Lewis acid catalyst back. And we're finished. So we have put an alkyl group onto the aromatic ring. Questions on that? Let's look at another example. We know Crafts is an important reaction, so we'll do another example. Take this alkyl halide. So I've got my aromatic ring. I have an alkyl halide. We're going to put in a Lewis acid catalyst. Any Lewis acid will work. I'll do iron bromide. If you notice what I've been doing, it's not a requirement, but most people just think it looks better. If you got a bromine here, we usually use like iron bromide or aluminum bromide. That's not a requirement. You can still use aluminum chloride or BF3 or any Lewis acid. Any Lewis acid will work. But most people just think it looks better to make them match. But it's not. That's not a requirement. They don't have to match. It would work with any Lewis acid. But most people just think it's prettier, I guess, to make them match. Okay, so I've got my alkyl halide, Lewis acid, and we're going to put an alkyl group onto the ring. Just like we did there before. There's my alkyl group. Does that look right? Okay. We don't get that. Why not? Let's go through our mechanism and see. Something didn't work right here for this reaction. In the previous one, we just stuck that alkyl group right onto the ring. So let's see what happens. Okay, mechanism is the same to start with. Alkyl halide. We're going to give electrons to the Lewis acid. So that part of the mechanism is the same. That bromine now has a full plus charge. That bromine's not happy. Being an electronegative atom, it wants a negative charge. Doesn't want a plus charge. It's divalent, doesn't want to be divalent, wants to be monovalent, wants one bond. So that's going to break apart. Give us the carbocation. We'll be left with this anion. And in the previous example, we added that carbocation was our electrophile and it added to the aromatic ring. But I just said that's not our product. What's the problem here? Watch for cation. Anytime you have a carbocation in a mechanism, watch for cation rearrangement. That is a primary carbocation. If you can get to a secondary or tertiary, it will want to do that because those are more stable. If you recall from Organic 1, primary carbocations can rearrange to a secondary. Secondary can rearrange, well, let me do one more. Primary can also rearrange to a tertiary. Secondary can rearrange to a tertiary. To do cation rearrangement, you must go to something more stable. Secondary to a secondary would never happen because I didn't gain anything. You have to gain something. You have to get to something more stable. Anything's more stable than the primary, so primaries will rearrange very quickly. If you recall our rearrangements, there's two rearrangements we can do. We can do a methyl shift or a hydride shift. Those shifts must occur from the beta position. Alpha is where the cation is. The next one out is beta. So we need to shift something from the beta position. That beta carbon has got hydrogens on it and it has a methyl group, so which one do I do? Well, you always do hydride first because it's a smaller group, easier to move. You only do methyl if you don't have any other option. If there was all methyls, then I would have to do a methyl shift. But we're going to do hydride first. It's a smaller group, easier to move. I'm moving a hydride over an H minus. From the beta position, we're going to move a hydride over H minus. And so that will give us our hydride shift here. That now gives us a secondary carbocation. That is more stable than the primary. So that rearrangement will occur very quickly because we're going to something more stable. Now there's no way I can get it to a tertiary. I don't even have enough carbons. Secondary is as stable as we can get. And that's what reacts with the aromatic ring. Now, everything's the same now. So that's our aromatic ring is going to give a pair of electrons to the electrophile. Now we need to get our catalyst back and we need to get the hydrogen off of the carbon where we just put our electrophile so that we can get that aromatic ring back. Right now we don't have the catalyst. We've got this anion back here. Let me redraw that. So we're going to take a bromine off to come and grab that hydrogen, and the electrons kick toward the plus charge to form the double bond again. So we get our aromatic ring back. There is our organic product. We also make HBr as a byproduct, and you get the catalyst back. So this one underwent cation rearrangement. So that's one of the bad things about the Friedel-Crafts alkylation reaction is that we must watch for cation rearrangement with these because there is a carbocation involved. So watch for rearrangement. So that first product I drew there a moment ago, we don't get any of that, or at least very little. Maybe you get 1 or 2%. This is going to be the major product where it rearranged. Questions on that? Now, normally most people use the alkyl halides for the Friedel-Crafts reaction. We can also use alcohols. Alcohols will also work for the Friedel-Crafts alkylation. So let's look at an example of that. Let's take our benzene ring. I'm going to choose this alcohol as my alcohol. Any alcohol would work. And we still need a Lewis acid catalyst. Now, for some reason, don't know why, But for alcohols, the BF3 works the best as the Lewis acid catalyst. The others can work, but for some reason BF3 just works really well with the alcohols. I don't know why. So most of the time you're going to see BF3 as the catalyst when you're doing an alcohol. These don't work quite as well as the alkyl halides, and so they're going to need some heat. We typically heat these 50, 60 degrees, something like that. I'll just put heat. Doesn't matter about the temperature, but we do need heat. And we will put the alkyl group on to the aromatic ring. As a byproduct, we would get water here. But we put the alkyl group on. Now let's look at the mechanism. The mechanism is the same as what we did with the alkyl halides. I'll do the mechanism up through till we get to the electrophile, and then I'll let you finish out because it's the same as what we were doing there before. So, first step, we got the Lewis acid. That boron has got a large partial positive charge on the boron. There's only 6 electrons around the boron, and the 6 that it's got, the fluorines are pulling them away. So it's a big partial positive charge on the boron. It wants some electrons. Well, they can get it from the OH group, or alcohol. That alcohol will give a pair to the boron. That leaves a plus charge on the oxygen. And that puts a negative charge on the boron. Now that oxygen with a full plus charge is a good leaving group. That's going to leave off. That gives us our carbocation. That is our electrophile. That is a secondary carbocation. There's nothing we can do to get it any more stable than the secondary. There's no way we can get to a tertiary. So it's stuck there. It's not going to rearrange. And we have that anion there. That we'll use later as a base. I said I wasn't going to finish it, but I'll go ahead and finish it. Let's take our carbocation. Take a pair out of the aromatic ring and give to the cation. There's our rhenium ion. We need to get our catalyst back. We also need to get our aromatic ring back. So we're going to take the OH off to come and grab the hydrogen. Electrons kick toward the plus charge. And that gives you the product and the water there as a byproduct. And we get our catalyst back. So we can also do alcohols. Alcohols will also work. Basically, anything that can form a carbocation will work for a Friedel-Crafts reaction. Let me give you another example of something else. We can do an alkene. Now for the alkene, we're going to use HF. I'm going to use HF because we need a proton, an acid to protonate. We need an acid to protonate the double bond. And then the fluorine anion is a poor nucleophile. So we need a poor nucleophile. I don't want the halogen to add to the cation. We want the cation to react with the aromatic ring. So fluorine is a very poor nucleophile. So this protonates the double bond That gives us the carbocation. That's our electrophile. And then that will add to the aromatic ring. I'm not going to go through the rest of the mechanism. We'll just put up the product. But you can get that alkyl group onto the aromatic ring. So you can use an alkene because we can make a carbocation out of that. So like I said, basically anything that gives a carbocation we can use in a Friedel-Crafts reaction. Any questions on that? Yes?
What about a carboxylic acid? Can you use that?
No. Carboxylic acid, there's no way to get to a carbocation with a carboxylic acid. I could use, well, that's not a strong enough acid to do the protonating, so I can't use the acid there, and I can't use it as this part to put that onto the ring, because there's no way to get to a cation. So no, can't do a carboxylic acid. Other questions? Okay, let's go ahead and take our break just a little bit early, because this is a good place to got a little bit different topic here next. Now, we just saw with the Friedel-Crafts alkylation that we had to watch for cation rearrangement. So I had up there a moment ago that one product that we didn't make. I had a big X through that one. We didn't make that one because it rearranged when we tried to make it. What if I really wanted to make it though? What if I needed that compound for some specific purpose? How can I make it? How can I avoid the cation rearrangement? And that's what we're going to be looking at next. One of the ways that we can avoid that rearrangement. We're going to look next at a Friedel-Crafts acylation. And I'll come back to that compound a little bit later. We'll learn how to make that using a Friedel-Crafts acylation. So this is acylation instead of alkylation. We're going to be putting an acyl group on. An acyl group is a carbonyl with an alkyl coming off of one side. This is an acyl group. We've talked about that before. It's got an abbreviation of AC. Sometimes we'll abbreviate it AC. That's an acyl group. So we're going to be looking at putting an acyl group onto an aromatic ring. To do that, we're going to take our aromatic ring and react with, I'm going to stay generic here, and then I'll do some specific examples. We're going to react with an acyl chloride. We're still going to need the Lewis acid catalyst. And any Lewis acid catalyst would work. And we will put an acyl group onto that ring. As a byproduct, we get HCl here as a byproduct. But we have put an acyl group onto the ring. Now let's look at the mechanism. The mechanism is the same as what we've been doing. I'll stay generic here for the mechanism as well, and then I'll put up a specific example. Let's write a Lewis acid catalyst here. I'll use aluminum chloride as my Lewis acid catalyst. So we have the acyl chloride and my Lewis acid catalyst. It's the same mechanism. We're going to give electrons from the chlorine on the acyl chloride. Those are going to be given to the aluminum. That will put a plus charge now on that chlorine. And a chlorine with a plus charge is not happy. And so this will want to break apart. We could break the chlorine aluminum bond. We go right back where we started. Or we can break the carbon chlorine bond. So you're going to take the electrons onto the chlorine. That gives us an acyl cation. And we also have the anion down here, the aluminum anion that we will need later to get the proton. But we've made an acyl cation. That acyl cation is our electrophile. Now, acyl cations are special. Acyl cations will not rearrange. Why will an acyl cation not rearrange? Resonance. It's stable because of resonance. We've got, let me just show you here. I'll redraw it and show you the resonance. We can draw resonance with the lone pairs on the oxygen. You can bring those electrons in and you can draw resonance. Now be a triple bond, but we're going back and forth between those two resonance structures. So that's a pretty stable carbocation because of the resonance. So that's why they will not rearrange. They are stable because of resonance. So acyl cations will never rearrange because they have the resonance. Now, that acyl cation is what is our electrophile. So that's what adds to the aromatic ring. So now the mechanism is the same. Same mechanism from here on out is what we've been doing. We'll take the electrons out of the double bond of the aromatic ring and add to the electrophile. So one carbon gets the electrophile, one gets a plus charge. I need to get the hydrogen off of the carbon where I just put the electrophile. I also need my catalyst back. We're going to take a chlorine off of this anion, come and grab the hydrogen, and the electrons kick toward the plus charge and reform our aromatic ring. And we put the acyl group on. There is our product. As a byproduct, we've just made HCl. Chlorine grabbed the hydrogen. I don't care about that. And we got our Lewis acid catalyst back. But there, here is our organic product. We have put an acyl group on to the aromatic ring. So let's look at a specific example. I'm not going to go through the mechanism again, but I'll put up a specific example rather than this generic. Taking benzene and I'll use this acyl chloride. Any acyl chloride will work. And we need a Lewis acid catalyst. Any Lewis acid catalyst will work. I'll use aluminum chloride. And so again, that's going to pull the chlorine off, give you the acyl cation. The acyl cation is what adds to the aromatic ring. And there's our product. Now let's do one more. I'll give you a hard one.